Welcome to today's Explainer. We're embarking on a truly massive journey today. We're going to explore the invisible systems that literally keep our lights on and keep the whole world moving. We'll be traveling from the incredibly massive spinning blades of a power plant all the way down to the microscopic chemical behavior of molecules in industrial oil. We are looking at the complete anatomy of power and how human ingenuity has completely mastered the art of harnessing energy. But before we get into the really heavy engineering, I want you to think about this question for a second. How do we actually capture the invisible forces of nature? Think about it. The wind blowing across a plain, the rushing flow of a river, or the immense, expanding pressure of superheated steam. Well, before we can plug in a smartphone or fly across the ocean, a raw physical force has to be tamed and translated into a usable format. And that translation? That is exactly what today is all about. Okay, let's dive into this. Here is our roadmap for today. First, we have the engine of civilization. Second, impulse versus reaction. Third, a turbine for every element. Fourth, designing with digital simulation. And finally, number 5, the lifeblood of turbines. Section 1, the engine of civilization, harnessing flow. Humanity has relied on turbomachinery for absolutely millennia. We've scaled up from ancient wooden water wheels on rivers to the modern, hyper-engineered megastructures that literally power entire cities today. And the word turbine actually comes from the Latin word turbo, which just means to whirl. Fundamentally, a turbine is a machine that converts a working fluid's kinetic energy, so its velocity, and its potential energy, its pressure, into rotating mechanical energy. You're basically taking linear throughflow, something moving in a straight line or expanding outward, and forcing it to spin a central shaft. And this brilliantly illustrates the physics at play. As noted by ANSYS, the blade is essentially a lever pushed on by the momentum and pressure of the fluid. By treating the blade as a lever, the fluid's force creates torque around that central shaft. So instead of pushing a clunky piston up and down, the fluid simply flows through, generating this beautiful, continuous, powerful rotation. That rotating kinetic energy can then be hooked up to an electrical generator, a propeller, or really any other system you can think of. Section 2. Impulse versus reaction. 2 ways to spin. Now, there are 2 primary strategies these machines use to extract energy from the fluid. First up, impulse turbines. These are driven purely by the fluid's momentum, its velocity. Just imagine a high-velocity stream of fluid acting almost like a hammer striking a series of paddles. A classic example is a Pelton water wheel, which actually doesn't even need an enclosure to guide the fluid after it strikes. But contrast that with reaction turbines. These are driven by a fluid pressure drop. Because they rely on extracting pressure as the fluid expands, they absolutely require a solid enclosure or casing to force the fluid through the blades. The massive wind turbines you see, or the gas turbines in jet engines, well, they operate on this reaction principle. Section 3, a turbine for every element, categorizing turbomachinery. The sheer versatility of turbomachinery across different working fluids is genuinely staggering. If your working fluid is water, you're utilizing gravity to run hydroelectric power dams. Steam? Well, that uses thermal energy from fossil fuels or nuclear reactors for massive electrical power plants. Wind turbines rely on atmospheric heating from the sun to power wind farms, and we also use compressed air to power high-speed hand tools. In fact, that drill your dentist uses is very often an air turbine spinning at unbelievable speeds. Finally, gas, driven by a combustion chamber, is what powers jet engines and automotive turbochargers. So from a dentist chair to a commercial air miner, turbines are everywhere. Section 4. Designing with digital simulation, the engineering journey. Now, you absolutely can't just guess when building machines that operate at these extreme speeds and temperatures. So, the engineering journey has shifted heavily into the digital realm. Platforms like ANSYS approach this simulation through a really cohesive step-by-step journey. First, they define the thermodynamic flow path. Then, they use computational fluid dynamics to map the 3D geometry of the blades and the stator. From there, they examine how the stationary and rotating parts interact in complex, transient flows over time. Once the fluid mechanics are dialed in, structural and thermal design tests those virtual metals against extreme cyclic loads and blistering temperatures. Eventually, they bring all these components together into one optimized system. Finding the perfect balance of cost, efficiency, and robustness, that requires immense computational power before a single piece of metal is ever even cut. Let's move to and see how this builds into Section 5, the lifeblood of turbines surviving extreme physics. Once these massive machines are physically built, we have to zoom in from the macro scale right down to the micro scale to keep them from literally tearing themselves apart. Take Turbine M from PTT Lubricants, for example. To survive the incredible heat, pressure, and friction of a spinning rotor, this highly specialized industrial oil is formulated with advanced additive technology to provide maximum oxidative and thermal resistance. This targeted chemical engineering extends oil drain periods, it offers excellent wear and corrosion protection, and it prevents sludge and varnish buildup. It perfectly meets the incredibly strict Mitsubishi standard specifications for gas, steam, and water turbines, ensuring that the physical hardware avoids a catastrophic failure. Now, what's really interesting about this slide is the KVT diagram, kinematic viscosity versus temperature, showing the performance curves for two grades of Turbine M. Notice how, as the temperature rises to extreme levels well over 100 degrees Celsius, the oil's viscosity elegantly smooths out rather than breaking down completely. It maintains a perfectly stable, protective film. This visually proves the oil's incredible stability across a massive range of totally punishing operational temperatures. So, the crucial point is that you can really see this molecular engineering at work in these extreme test characteristics. The flash point, which is the temperature where the oil vaporizes and can ignite, is a staggering 242 to 250 degrees Celsius. Conversely, its pour point is -12 degrees. It perfectly passes rust prevention, and its water separation test results in a perfect 40-40-0 score. That means it rapidly separates from water, which is absolutely critical for steam and water turbines to prevent emulsion. Designing the molecular structure of the oil is just as vital as simulating the aerodynamic curve of the turbine blade. Both the macro and the micro are entirely required to keep civilization running. Which leads us to our final thought for today's explainer. The next time you flip a light switch in your home, or board a commercial flight, or even, sit in the dentist chair, ask yourself, what invisible engineering is spinning right now to make this possible? Our modern world is fundamentally built on the back of the whirling, highly engineered magic of turbomachinery. Thanks for exploring the anatomy of power with me today, and never stop wondering about the hidden mechanics spinning in the background of your daily life.